Okay, so our last section in this chapter, chapter 4, is on exponential and logarithmic models. That means we're going to be dealing with a lot of word problem, situational type stuff that deals with what we've been talking about in the other lessons, the exponential equations and the logarithmic equations. Like I mentioned last week, this will not be specifically on the test. There is one extra credit question. It can't count against you. If you want to try it, go ahead. If not, you just skip it. And like I said, it doesn't count against you. It's just extra credit if you get it. That will come from this section. There will be an assignment. So that's the only thing you've got for this week is the assignment over this. It's not going to be super long or anything, but there will be an assignment over that just like normal. And then that'll be due next Monday, just like previously. And then next week, we cover, we're only doing 2 sections in chapter 8. Section 8.1 and 8.7, which is on systems. And then the following week, we take our test over that. And then I'll give you some information about the review after that test or before the test, whatever. And then the following week is our semester final. You guys are almost done. It's going to go really quick from here on out. So let's get into this, and then we'll get to our test and get you guys out of here tonight. So exponential and logarithmic models. The first topic we want to discuss is what is called radioactive decay. And radioactive decay are when radioactive substances break down over time. They give off electrons and they break down into other substances. And so they have what is called a half-life. And this is going to be a very important term, so make sure you mark that. A half-life. So the half-life of a radioactive substance, radioactive isotope, is the time it takes for half of the substance to decay. So let's say that a substance has a half-life of 5 days. If it starts out with 5 milligrams of that substance, after 5 days, now I don't remember how much I said. Let's say we start out with 10 milligrams of that substance. After 5 days, there's only going to be 5 milligrams left because half of it went away. After another 5 days, there will be 2.5 milligrams left because it keeps breaking in half every 5 days. So after another 5 days, 1.25 milligrams will be left. Okay, so it doesn't ever, in theory, it doesn't ever completely vanish. Now, practically, you get to such a small amount, you can't really measure it. But in theory, it never completely goes away. It's just always half of what it used to be. Okay, so that is a half-life of a radioactive isotope, and we're going to talk about those half-lives as we go through the night tonight. So here's our first example. Bismuth-210 is an isotope that decays by about 13% each day. What is the half-life of bismuth-210? So when we're looking at this, things that decay and break down are doing that at a continuous rate. It's not like it waits till the end of the day and then poof, 13% is gone. It's breaking down throughout the day as well. Does that make sense? So anything that we deal with that has that continuous change, if you remember, that's the equation. Excuse me, that's the equation. Y equals A times E, and I think it's RT, but I can't remember. You got the exponent for rate and time. Okay, so notice in this case, they don't tell us how much bismuth-210 we have. And also one other thing I'll point out is the 210 is part of the name. It is not telling you how much there is or anything about the problem. It's just part of the name to differentiate it from other bismuth isotopes. So the bismuth-210 is what we're talking about. They don't tell us how much there is or anything like that. So my suggestion is when you have a problem like this, make your starting amount, your A value, just make that 100%. So just make it 100. It makes it easy to work with. So we've got our 100. And it really doesn't matter what we choose, but I think that 100 is a very easy number to work with. So 100, then we have E. We don't know what R is. Oh, actually, sorry, we do know what R is because they told us. A lot of times we don't. I was doing a problem with my college algebra class in high school, and a lot of them we didn't know what R was. But in this case, they do. We do know what R is. It's 13%. So if it's breaking down, it's getting smaller over time, right? It's decaying, it's breaking down, there's going to be less of it. So what happens if you've got 13% going away each day, you put in a negative 0.13. Okay, are we okay with that? Remember that 13% is 0.13 as a decimal. Okay, and then since it's decaying and it's getting smaller, that's where the negative comes from. Okay, so that's where the negative 0.13 comes from. The time is what we don't know. Half-life is an amount of time, how much time it takes for half of it to break down. All right, so since that's what we're looking for, and we want to know how much time it takes for half of it to go away, what do you think we might put over here as our new amount? Any ideas? 50, because why? If we're starting with 100, half of that is 50%. Okay, and so on most of those half-life problems, that's how we can kind of set them up that way. So now our goal is to solve this. And what type of equation have we just set up here? What type of equation is this? Is it going to be exponential or is it going to be logarithmic? Or I should say, is it exponential or is it logarithmic? Yeah, why? Say that again. The E, it's actually not the E, it's actually the T. It's where the variable is, and the variable is in the exponent, so that makes it exponential. If the variable is inside the log, then that makes it logarithmic. Okay, so it's exponential, and we've been talking about exponential the last couple of weeks. If you remember your steps, the first thing you're always going to do is isolate, and our base is E, our exponent is that stuff right there, and we want to isolate that, which means we have to get rid of what? We're going to get rid of the exponent, but not quite yet. What's to get this by itself? What do we have to get rid of?
Divide 100.
Yeah, we have to get rid of the 100. And you're right, we're going to divide it because it's multiplying 100 times that. So we're going to divide by 100 on both sides. So that cancels out. And so all we have there is e to the negative 0.13 times t equals, and this is going to be 0.5. Okay. Then, so we've isolated. What's the next thing we do for our exponential equations? This was the big one. This was the most important one because this is how we deal with it. And I hope you're just being shy and bashful and that you actually know this because it's important for tonight's test. So for an exponential equation, the most important step here once we get to this point is we're going to take the log of both sides. And in this case, we're going to use natural log. So I'm going to go ahead. I'm just going to switch colors here. And I'm going to put natural log right here in front of this one and natural log here in front of that one. So we are going to have natural log of 0.5 equals, and does anybody remember what happens when you have a natural log next to an e? They cancel out. That's especially why we would use natural log in this case. They cancel out, and we have negative 0.13 t. And so what will our last step be? So that natural log of both sides, that's how we get the t in a spot where we can work with it. So what are we going to do now to finish solving for the t?
Divide both sides by 0.13.
Yep, that is correct. Divide both sides by the negative 0.13. That cancels that. Okay. And at that point, you're just going to take your calculators. And again, you can do it one step at a time. If you decide to try and do it all at once, just make sure you're careful with your parentheses. But we need natural log of 0.5. And then once we have that, we're going to divide that by negative 0.13. And what do we get for our t value? Anybody got it? I see a lot of calculators working. Some calculator has to give you the answer, right?
5.3319.
Okay, 5.33, and we'll probably round it up to 5.332. And the units here, because it says it's decaying about 13% each day, the units here are days. So after a little bit more than 5 days, that's how long it takes for half of that substance to break down. Okay, does that make sense? All right. So again, the extra part that we're doing tonight is we're setting up the equation ourselves, whereas on your test, the equation will already be there. You're just going to solve it. But here we have that extra step of setting it up. But after we set it up, it's all what we've been doing the last couple of weeks. Okay. So about 5 days, 5.332 is our answer there. Any questions on that one before we go on? You remember that main step of taking the log of both sides, hopefully? All right. So next one, cesium-137 has a half-life of about 30 years. If you begin with 200 milligrams of cesium-137, again, the 137 is just part of the name, how much will remain after 30 years, after 60 years, and after 90 years? So this one, if you notice, 30 years, 60 years, 90 years, the half-life is 30 years. This is just a concept question, right? So here's how I want us to think about it. At time 0, mass, we'll just put M down here, M of T. How much do they have at time 0? How much do they start with? 200 milligrams. After 30 years, how much will they have? 100, because why? Yeah, 30 years is the half-life, so that's how long it takes for half of it to go away. So after 30 years, you're going to have 100 milligrams. 200 times 1/2, or divided by 2. Well, then what about after 60 years? How much will be left? 50, because, again, half, right? So 50 milligrams will be left after 60 years. And then after 90 years, how much will be left then? Not none, because it's not subtracting 50. It's taking half. So it's going to be, yeah, it's going to be, does that make sense?
Yes.
So it's going to be 25. So it's always taking half of what you had before. Does that make sense? So if you remember what that picture looks like, you're starting with a lot and it's shrinking fast, but then it starts slowing down as it shrinks. That's kind of the idea. Since there's less of it to decay. Okay. So that's the idea. And so that's just a concept question. If you know the half-life and I give you multiples of that half-life, you can generate the masses for those 3 years, 3 sets of years. Does that make sense? Okay. Let's take a look at another one, carbon-14. And I apologize for those of you who weren't here earlier. I've got allergies or something, and it's stuck right here behind my nose and tickling my throat. And so my voice is a little bit not quite there tonight, so bear with me. But anyway, example 4, we've got carbon-14. It's a radioactive isotope that is present in organic materials. It is commonly used for dating historical artifacts. Carbon-14 has a half-life of 5,730 years. If a bone fragment is found that contains 20% of its original carbon-14, how old is the bone? So let's go back. Remember, we're dealing with this same equation. These things break down continuously. So A, E, R, T. And let's see what we know. And this one is going to be a little bit tricky. So the reason it's tricky is because remember last time they told us the rate, it was decaying 13% each day. Did they tell us the rate here? No, they didn't say it decays a certain percent or grows a certain percent. They didn't tell us that. What they did tell us was the half-life. Based on the half-life, we can figure out what the rate is. Okay, so this is actually a multiple step problem. First step is to figure out the rate, and then we can go back and answer the question that they actually ask. Okay, so first step is we've got to figure this out. So here's what we know. Do we know the starting amount? No, but we do know that we're talking about percentage. So what's a convenient percentage to start with for our starting amount? 100%. Okay, we're starting with all of it. And we have E. E is just E. We don't know what R is. And here's where we're going to use this information about the half-life. The half-life is 5,730 years. So that's the time that we're going to put in. And if we go that much time, how much will be left of our original 100%? Sorry? 20%. Not 20. You're one step ahead. We're going to get there, but we're not ready for that yet. So 5,730 is a half-life. So by definition, what does that mean happens to the 100? 50. Half of it is left, right? So this is our first step, is we're going to figure out what R is. And notice this equation looks a lot like that last one that we, not the last one, but the first one we did. So what do you think we should do first? Sorry?
The log.
Not quite yet. We've got one thing to do first.
Divide both sides.
Yeah, we want to isolate our exponential part. So we're going to cancel out the 100 by division. That's right. And remember, we got 0.5. And we have E. And then I'm going to rearrange that. We like that a little bit nicer if it's 5,730 R. And now we're ready for U. We're going to take that natural log of both sides, right? So I'm going to switch colors again. So natural log on both sides. So we have natural log of 0.5. And then this cancels, remember, the natural log and the E together cancel out. And we have 5,730 R left over. Then how do we finish figuring out what R is?
Divide both sides by the years.
Yep, 5,730. Now, that's going to give us a really small number. And so if you guys could do that for me, my suggestion would be keep at least 5 or 6 decimal places on your rate. Because especially if your half-life is like thousands of years, that rate's going to be a pretty small number. Okay, so what are we getting for the rate? It's probably a lot of zeros. It's probably negative and a lot of zeros.
Negative 1.2096.
Is there an E after your number at the end or something like that? Can I see it?
Yeah.
Yeah, that times 10 to the negative 4. So yours doesn't have E, yours has. So what that, so tell me that number again.
1.2096.
And then her calculator actually says times 10 to the negative 4th. Some of yours might say E negative 4. This is scientific notation. That means it's a really small number. So actually, this number is, it's smaller than this. And the negative 4 tells us we're supposed to make it smaller by 4 decimal places. So what happens is we move our decimal place over 1, 2, 3, 4 times and fill that in with zeros. So this ends up being negative 0.00012. And that's why I say we got to keep at least 5 decimal places. Otherwise, it just looks like a 0, right? So that's our rate. And like I said, especially with those thousands of years, they're going to be really small. So that's going to be our rate. Is everybody okay with that on their calculator, what their calculator shows when they have that scientific notation? Make sure you look for that, especially in a problem like that on your homework, because it will pop up once in a while. So that's part 1 of this question. We found the rate. Now we have to go to the second part. How old is the bone if it contains 20% of what it originally contained? So we go back to the beginning. Again, what are we using as our starting percentage amount? 100. Then we have E, and then we know what R is this time. It's negative 0.00012. And this time we're actually how old? We're trying to figure out the time, right? So it's a whole new question. They told us the half-life right away so we could figure out R, but now we're supposed to figure out how old is this bone that has what goes over here. Now we're ready for your answer. The 20, right? because there's only 20% left. Okay, so again, doesn't this equation look really similar to wherever this one that right here? We just have to solve it twice, once to get the rate so that we can go on and find that how old is this bone that only has 20% left. So again, it's kind of repeat. What do we do first? Isolate. So we're going to do what? Divide by 100. And that gives us 0.2. And then we've got the rest of that stuff still. And what are we going to do after that? The main step for exponential equations?
The natural log.
Yeah, and again, you can use any log, but for us in this problem with the base of e, natural log is much more convenient because it's going to cancel. So natural log of both sides. So that will give us natural log of 0.2 equals, this cancels, negative 0.00012 t. And then what is our last step going to be?
Divide both sides.
Yep. Get the t by itself. We've got to divide by this. And what do we get when we take natural log of 0.2 divided by negative 0.00012? And it's going to be a pretty big number. 13,400. And this is years, right? Now, here's the thing with a question like this. When you're talking about that many years, are we going to probably give an answer that looks like this? Do you think any scientist really thinks it's exactly 13,411.98 years old, years ago? No. In fact, they're usually very careful to generalize and give themselves even a range. But what we would say is probably, I mean, you could probably say between 13 and 14,000. You could probably say around 13,400, but you probably wouldn't be any more specific than that. You might even just say, oh, it's around 13,000 because it's an estimate, right? For a couple of reasons. I mean, we say it has 20% as much carbon-14 as it used to, but do we actually know how much it started with? No. We say the half-life of carbon-14 is 5,730 years, but was anybody of us around 5,730 years ago to be able to actually measure it, to see? No, it's all calculations that we've done as mathematics people and scientists to figure this stuff out. But when those numbers are that big, it's really hard for us to be absolutely sure. So they have to give estimates on situations like that. Okay. But we're looking at about, and I guess I've got about 13,300. That maybe if we use, if we don't round this number off, because we did, if you remember, we did round that number off a little bit. But again, you're around that 13,000 range. Okay. So we got two equations out of that one. On your homework, I know there will be some problems where you do have stuff like this, where you have two steps. You've got to find the R value first because they don't give it to you. And then you have to use that R value to help you figure out a second answer. And that's the answer you're actually looking for. So make sure you kind of look out for those as you're going through. Any other questions on that one? All right, a blank screen, okay? Doubling time. Well, you may guess that half-life and doubling time are kind of similar. What do you think doubling time might mean? Well, since it's written right here, it's the amount of time that something takes to double in size, right? So it's going to be the opposite. This one is growing now instead of shrinking. Okay, so doubling time of a growing quantity is the amount of time it takes for a quantity to double. And for all of us, we hope that's our money, right? But that's what it is. A lot of times we talk about that. This is not one that we want it to be, but it happens sometimes. Cancer cells sometimes increase exponentially. If a cancerous growth contains 300 cells last month and 360 cells this month, how long will it take for the number of cancer cells to double? So again, we're being given some information to figure out R so that we can eventually figure out how long it takes to double. This is going to be another one of those two-part questions. So our equation is still the same, A, E, R, T. Okay. What information do we know from what they gave us? Do we know the, let's say the A is usually where we start. Do we know the starting amount?
300.
300. Okay. So 300 is our starting amount, A. E is just E. Did they give us a rate? No, I gave that away already because I said we had to figure it out. But rate, we don't know. Did they give us a time?
One month.
1 month, because they said last month and this month, right? So that's your 1 month of change. So that's kind of nice because it's just a 1. So we have to remember our unit of time is months. And then the last thing is that 360, that's going to have to be our new amount, right? Over here on this side, that's the new amount. That's 360. So this is going to look very similar to the problem that we were just doing because, again, it's exponential with a base of E. It's a continuous change. So what should we do first? Divide by the 300 on both sides. That's correct. That'll cancel. This one will reduce. Let's see, can divide by 6. So this ends up being 1.2. And 1 times R is just R. So I'm just going to write E to the R power. And then what else do we have to do? This one is going to be a little bit shorter. Yeah, natural log of both sides. And in this case, we get natural log of 1.2 equals, and this cancels, we just get R. So we're really done. And honestly, if I can leave it and it's this short, I would just leave it like this. Now I could divide that, or not divide it, but put that into my calculator and have 5 decimal places. But it's actually shorter to type this into your calculator than that 5 decimal places of stuff. Okay, so I would just probably leave it like this. And so what that tells us is we're starting with 300. We've got E. We know that R is the natural log of 1.2. We know we're going to have time and we're going to have the new amount. So that's our equation at this point. We now that we know R. So now we have to go on to the second part of the question. How long will it take? So what is our answer going to be if they're asking us how long? How many months? It's the time, right? How long will it take for the number of cancer cells to double? And here's where you have to be careful. What was the starting amount of cancer cells? 300. If it doubles, what's the new amount going to be? 600. I have a lot of people that want to double this. That makes sense? And you actually can do it that way, but it makes it more complicated. So I would say just go with this. This is your starting amount. To double it, you're going to have 600. And we're trying to figure out what T is. So again, it's the same type of thing, right? What are we going to do next? Divide by 300. So this is now a 2. E, natural log of 1.2 times T. What are we going to do after that? Natural log of both sides. So that will cancel. And we will have natural log of 2 equals natural log of 1.2 times T. And how do we finish this one up? You're one step away. Divide by, to get the T by itself, divide by natural log of 1.2. Cancel that. So T equals, and
31.284.
say it one more time.
31.2841.
Okay. And again, I should be careful when I say this because I know I said with that time that we did the 13,000 to make sure you round off, because in reality, that's what they do. On the computer, they might want you to be more specific. So you might have to actually put in the actual number you get. Okay. So just be aware if they say to round to a certain place. To me, I'm looking at this and I would probably round it off. Let's see what they had for, or see what I had for an answer if I did 3 decimal places. So, oh wait, I've got something going on here. Did everybody get to 31?
No, I got that.
Get 3.8?
Yeah.
Okay. So we're probably good with that 3.8. Did you, let's take a look at what you got. Oh, it's because this should be just a 2.
Oh, crap,
Because that,
yeah.
that divided. But yeah, that would be a really big number then.
Okay, yeah, that makes sense.
You got that 3.8 now?
Yes.
Okay, good. So 3.8 should be our answer there. That's why I have the answers up here, just to catch my mistakes if I make them. So, okay. Does that make sense? Doubling time. It's really, all of these equations are going to be the same thing we've been doing. You do them very similarly. It's just a matter of different applications of them. Okay. I'm going to skip that one. I want to get to this one, which is the logarithmic. I don't want to get you guys completely burned out before your test, so I want to make sure we hit some exponentials, which we have done several already, and then some logarithmic. So earthquakes are measured with what is called a logarithmic scale. So for an earthquake with a seismic moment, which they call S, a measurement of earth movement, the MMS value, or the magnitude of the earthquake, is M equals 2/3 log of S divided by S sub 0. And then they tell us S sub 0 is 10 to the 16th power. And the reason that they do, and it's a baseline measure for the seismic moment. The reason that they do this is because the amount of energy it takes and the amount of energy that's released in an earthquake is so huge that for us, it's really hard to comprehend the size of those numbers. So they boil it down with this logarithmic scale, which makes everything much smaller. And so then we can kind of compare and do stuff like that. So that's one of the things that we're looking at. Either really, really small numbers or also really, really big numbers tend to get logarithmic scales attached to them. So here's our equation again. If one earthquake has an MMS magnitude of 6 and the other one has a magnitude of 8, how much more powerful in terms of earth movement is the second earthquake? So what we have to do is we have to put these numbers into this equation, one for one earthquake and one for the other. So we have 2 separate problems, and then at the end, we're going to compare them. Because the question is, how much more powerful was the second one with that magnitude of 8 compared to the 6? And it's kind of interesting what we get for an answer here. So M, the magnitude, is for the first earthquake is 6. So 6 equals 2/3 log of S divided by, and do you remember they told us what S sub 0 was? It's 10 to the 16th power, right? If you look back in your notes there. So I'm just going to go ahead and put that in. It was 16, right? Okay. And then for the other one, we're going to do the same thing, but this time it's 8 equals 2/3 log of S over 10 to the 16th power. Okay. So looking at that, these are both logarithmic equations. And we know that because our variable is here inside of the logarithm on both of them. Okay. So the first step is still, we've got to isolate. Only this time we're isolating the logarithm, which is this part right here and this part right here. So what do we want to do first on each of these? Yeah, and we can divide by 2/3, and with a calculator you can do that. By hand, it's easier to multiply by the reciprocal. So I'm going to multiply by 3/2, and that cancels that out. And when I multiply 6 by 3/2, we get 9. And so now we have 9 equals log of S over 10 to the 16th. All right. Now, does anybody remember, now that we've moved on to logarithmic equations, does anybody remember our main step for solving a logarithmic equation? For exponentials, it was take the log of both sides. For logarithms, it's different. Anybody remember that? Well, it's a good thing we're reviewing it then. You want to rewrite the equation, the logarithmic equation, into exponential form. And remember, when we do that, we identify the base first. So what is the base of our logarithm here?
10.
10, because there's nothing written there. It's automatically a 10. And then what's the exponent for that 10 going to be? The 9. And then that will equal s over 10 to the 16th. And then to finish getting that s by itself, what do we have to do? Because it's being divided, we have to multiply by 10 to the 16th. So that will cancel. We have to do the same thing over here. What's the rule when we multiply numbers that have the same base and they have exponents? What do we do with the exponents? Add them. So this becomes 10 to the 25th power equals s. And we're just going to leave that right there for now. That's the smaller earthquake. But I'll tell you, 10 to the 25th power is a really big number. Okay, if you put that in your calculator, it's very big. Okay, so now let's do this one. The steps are exactly the same. So the first thing we're going to do, multiply by the reciprocal, 3/2. To cancel that, that's going to be 12. Okay, and what should we do next? I'll give you a hint. We did it over here on this side because it's going to be the exact same steps. Correct. And when we do that, we want to identify the base. And what is the base? 10. And that's going to be 10 to what power? Correct. Equals the s over 10 to the 16th. And just like last time, what are we going to do to finish getting that s by itself? Yep. Multiply by 10 to the 16th power on both sides to cancel that out. And again, we're going to add these exponents. So we get 10 to the 28th power. All right. So now here's the thing. When you say how much more powerful, a lot of times when we talk about this, we talk about how many times more powerful something is, or how many times, like if I said, oh, how much older am I than you? Well, you might say a certain number of years, or you might say, oh, you're twice as old as me, or 3 times as old as me, or whatever. Okay. So when we do that, when we talk about how many times more, we just take the big number and divide by the small number, and that tells us how many times more. So for us, the big number here is 10 to the 28th power. The small number is 10 to the 25th power. And so we've talked about the rule for multiplying when bases are the same. What's the rule for dividing when bases are the same? We subtract them. So this becomes 10 to the 3rd power. And what is 10 to the 3rd power? You can use your calculator for that. Or if you just know. The second earthquake was 1,000 times more powerful. That's why they boil that stuff down to a magnitude of 6 compared to a magnitude of 8. Because again, these amounts of energy are so incredibly large that for us to look at them, we don't get a real good sense or a real good feel. So just to kind of compare, we've got that magnitude of 6 on this scale compared to the magnitude of 8. The 8 is 1,000 times more powerful than the 6. Okay, so that shows you how much bigger and how much more energy we have being released there. So do we remember that now that we've refreshed a little bit on how to solve logarithmic equations? You still isolate first, but then your main step is to rewrite from exponential form into rewrite from logarithmic form into exponential form. Okay, so it's 1,000 times more powerful. And like I said, there's a few problems for you to do. Be on the lookout for those ones where it has 2 parts, where you have to figure out the R value first and then answer the question. because there probably are a few of those. That's the end of the lesson.